So one application that we can look at that occasionally comes up are density problems. Now, I know in physics, you usually talk about density being mass per unit volume or something. But density for us can be any kind of density. Okay? So let's look at some example problems. So here, a precinct of a city has one boundary along a river as shown in the figure at right. The population density of the city at any point along a strip x miles from the river's edge is f of x persons per square mile. Now, what the heck are we talking about there? We're saying that if we take, if we go 2 miles away, for example, and take a little strip out of that the density of that strip is going to be determined by f of 2. Okay? So a thin strip parallel to the river has thickness delta x. What is the area of this strip? Well, what is the area of that strip?
Is it the integral?
No. Just, I want the area of that strip.
Delta x times 3?
Yeah, delta x times 3. All right, since the population density is nearly constant on this strip because it's a narrow strip, the distance from the river has not changed much. What is an approximation of the population of this strip? Well, it would be f of x times, that would give you the density. So that would be how many people per unit area. And this gives us the unit area. So times 3 delta x. So then what would be an expression for the population of this entire precinct? Well, what we would want to do is we would want to divide this up into a whole bunch of little strips. Multiply 3 times f of x times delta x, and then add all those together.
So would it be 3 times f of x times the integral from 0 to x?
But f of x is changing. So you're close. It would be the integral from 0 to 6. So 0 miles from the river until you get to 6 miles from the river of 3 times f of x times dx. This would break this into an infinite number of tiny little strips, and the integral adds all those together. This is the idea behind an awful lot of problems. You break it into one small strip, figure out, well, how can I find what I want from that? And then I want to add all those together, so I'm integrating. Okay? That's the basic idea. So, for example, a sample of mold growing in a laboratory spreads out in a circular pattern. So this is going to be a little different than the last one where it was a rectangular pattern. The density of mold, spores, in spores per square millimeters, that should be spores per square millimeter, singular, not plural, is approximated by 1,000 times 20 minus t, where t is the distance from the center of the mold sample measured in millimeters. All right, so some questions. What is the radius of the mold sample? And at first you may think, they didn't tell me that, but they did indirectly. Is it possible for the density of the mold spores to be negative? No. Where would the density of the mold spores be 0? Nope.
The radius is less.
When the radius is less than 0. Think about that for just a second.
And there would be no circle, so there could be no
Yeah.
spores.
When is this equal to 0?
At 20.
At 20. Oh! So when it gets to 0, that's when you're out of mold spores. At the center, when t is equal to 0, you've got 20,000 mold spores per square millimeter. You have a lot of mold spores in the middle. And as it goes out, the density decreases. So it's 20 millimeters. A thin ring around the center of the mold has thickness delta R and radius R. So we've got this thin ring. Like that. So this is R, and the thickness is delta R. Everybody with me? All right, if we were to cut that ring and then straighten it out, what would be the area of the ring?
That would be 1,000.
Has nothing to do with this.
No. Delta R times R.
I'm sorry?
Delta R times R.
No.
Pi R times delta R.
You're getting closer.
So that's something to do with the circumference.
It does.
Okay.
What is the formula for circumference?
Oh, pi times 2R.
So 2 pi r
Yeah.
times
delta R.
delta r.
Because isn't circumference pi times diameter?
Yes.
Okay.
Or 2 times pi times the radius. So now write a formula to approximate the number of spores in this strip. So the number of spores in that strip would be approximately equal to the area times the density. So 1,000 times 20 minus r times 2 pi r times delta r. So this is the density times the area. Right, which makes sense. That's going to give you the number of mold spores. So the total number of spores how are we going to add those all together?
Integral from 0 to 20 of 2 pi R times 1,000 times 20 minus R.
Exactly. dr. The delta r gets replaced with dr because instead of having a thickness, we have some infinitesimally small thickness.
So we're basically taking the density of the strip and putting it into an integral.
We're taking the area of that strip times the density, which gives you the number of spores, and integrating that because we want to, basically what we're going to do is take the whole circle and break it into a bunch of rings. So let's see, that would be 2,000 pi times the integral from 0 to 20 of 20r minus r squared dr. And you could do that on a calculator. Let's go ahead and do that real quick.
A lot of spores.
Yeah. So 2,000 times pi times the integral from 0 to 20 of 20x minus x squared dx. Yeah, that's a lot of spores.
8 million something?
Yep.
Probably good for your health too.
Yeah. And that's 20 millimeters. So that's 2 centimeters. So the whole thing is about that big. Okay, any questions about that? All right, moving on. This is, if I recall correctly, an old AP problem. A city is built around a circular lake that has a radius of 1 mile. The population density of the city is F of R, people per square mile, where R is the distance from the center of the lake in miles. And which of the following expressions gives the number of people who live within 1 mile of the lake? All right, so we've got a lake.
You live within 1 mile of the lake. When you be in
No, 1 mile of the edge of the
beyond.
lake.
Okay.
So you've got, yeah. So again, a strip would have area 2 pi r delta r, right? So we know we're going to have 2 pi r dr in there. So the area of a strip, and that's always a good way to think about these, is 2 pi r times delta r. So we just want this part out here, right? So what is that going to affect? Exactly right. Our limits of integration are going to be from what to what?
1 to 2.
1 to 2.
So you can cross out it.
And you're like, okay, well,
Very good.
yeah, A through C are gone already.
My final question.
And we want 2 pi r delta r times f of r. Oh, well, that's just D. Okay? All right, moving on. So the density of cars in cars per mile down a 20-mile stretch of the Pennsylvania Turnpike can be approximated by, I'm trying to remember what letter that is. I think that's a rho. Anybody up on their Greek letters? I used to be.
You can join a fraternity or something? No.
Is equal to 300 times 2 plus sine of 4 square root of x plus 0.15, where x is the distance in miles from the Breezewood Toll Plaza. Find the total number of cars on the 20-mile stretch.
Who is this board?
Traffic engineers.
Yeah. Kind of an ugly equation.
Yeah, and basically what's happening is that you've got a sinusoidal function. So it increases, decreases, increases, decreases, all that kind of good stuff. So if this is the density, where x is the distance from the miles, so then we're just going to do the integral from 0 to 20 of rho of x dx. So grab a calculator for that. So 11,512.851 cars.
That's a lot of cars.
It's a 20-mile stretch. But that's like 5,000 cars per mile.
Yeah, that's a lot. 5,000?
Oh no, sorry. If you divide that by 20,
500-ish.
500 and change per mile. That's not as crazy.
I wonder why there's global warming.
Well, I suppose we could always ask Thanos to fix it for us.
I think he was right. If you kill half the universe, a lot of problems will be solved.
Yeah, it would replace it with a whole lot of other problems. All right. So let's look at this one. The density of oil in a circular oil slick on the surface of the ocean at a distance of r meters from the center of the slick is given by this expression, 50 over 1 plus r kilograms per square meters.
Is a slick just a mass of oil sitting on the surface?
Yeah. Yeah, oil tends to sit on the surface for a while, and then it because it's heavier than water, it tends to start globbing together and going down. Find the mass of the oil slick given that the radius of the slick is 10,000 meters. Okay. So notice this is kilograms per square meters, so we need to multiply this by the number of square meters in a particular slice of it. Well, again, the area of the slice is going to be 2 times pi times r times delta r, right? So then the mass is going to be the integral. And again, we have to go, well, all right, the density of an oil slick, it doesn't tell us how far this goes. Oh, but it does tell us here. Okay, so this is going to be from 0 to 10,000 of 2 pi r times 50 over 1 plus r dr. This is going to be a lot of oil. So 2 times pi times x times 50 over 1 plus x dx
Hard problem.
138,699.108 kilograms.
How many pounds is the kilogram?
Is a kilo like 2 pounds? That seems to be, I mean, that's a very rough approximation. If I remember correctly, I can never remember which way it works, but I'm pretty sure that a kilo is almost 2 pounds. We'll look it up in a minute.
I wish we were on the metric system.
There are days when it would be nice. Within what distance r from the center of the slick is half of the oil contained?
Oh,
This is a more difficult problem. So if we take half of this, 3,138,699.108 divided by 2 should be equal to the integral from 0 to some distance that I don't know, I'll call it x, of 2 pi r times 50 over 1 plus r dr. And I want to try and solve that for x. These kind of problems used to show up on the AP exam very regularly. I haven't really noticed them so much anymore, but where they would ask you to solve for one of these, to solve for a limit of integration. We haven't done one like that, I don't think. So let's see. That's going to be 100 pi. So the first thing I'm going to do is pull out the 100 pi and divide both sides by the 100 pi. So that's going to be the 3,138,699.105 divided by 200 pi is equal to the integral from 0 to x of r over 1 plus r dr. And the question becomes, well, what the heck are we supposed to do with that? I'm sorry? Yeah, and the question is, how do you find the antiderivative of that? Nope, u substitution is not going to be helpful on that. Because if I let u be equal 1 plus r, du is going to be just dr. Oh, we'll have to do this on Wednesday.
Do we have a lesson tomorrow?
Tomorrow, yes.
I always have a lesson.